Astrophysics and Cosmology assignment. The question 5 we'll solve today, 5 and 6. In question 5, Hipparchus satellite was the first satellite used to determine accurately the position of stars. Data for more than 100,000 stars was collected using a parallax method. What is a parallax method, or what is a trigonometric parallax? So what we do, like example, in a trigonometric parallax, the parallax is like apparent change in position of a star or object relative to its background. Like what actually happened, we focus on one of the star and its background, because when two objects are moving, like example, object A and object B are moving and we are observing both of them, the object will, if both are moving even with the same speed, but what it appears that object A is moving relatively faster as compared to B. So B is like, because if it is far, it appears that the distance it covers is negligible. So same idea in a trigonometric parallax, what we do, we consider like the background stars are there and we focus on one of the star and determine its change in the angle for a duration of a 6 month. And if we know that this D is there, this one is R and theta, so we can work out the distance between the Earth and that star. That is a trigonometric parallax. So, but what is meant by the term parallax? So the term parallax means like it's an apparent change in position of an object relative to its background. So change in position or apparent change in position of star compared to its background, that is known as the parallax. Or we also say trigonometric parallax if we use the angle and observe for a duration of a 6 month. A star is twice as far from Earth as star A is actually twice as far as from Earth as compared to star B. Describe what would be observed when trigonometric parallax used to determine the distance of these stars from the Earth. Like we have two stars, so these are the Earth, and we have two stars. Star A is twice far. So star A is, in this question, the star A is twice far as compared to star B. So how we can determine, like, describe what would be observed when the trigonometric parallax is used to determine the distances of these stars from the Earth. So if you want to determine the distances of these stars from the Earth, so we'll observe them and there will be background stars. Like these are representing the background stars. So we'll observe them for a duration or a period of a 6 month. And when we observe them, what will happen? Because for B, it is closer to us, so it appears, even though they are moving at the same speed, but B, it will appear apparent distance or change in distance for B, it appear to be more than A. So when we observe the change in angle for a duration of a 6 month, like example, if we observe this in Jan and we observe this in after 6 months, in a month of July, example, if we observe. So what we'll observe, the change in angle for B, it will be approximately twice as compared to change in angle for A. So if this was A, when we observe, so the angle which has changed for a duration or a period of a 6 months for B, it is approximately twice as compared to a angle change for A, because A is far from us, so relative or apparent motion of A or apparent distance covered by A will be shorter as compared to that of B. Or we can also say the angular position of A will be half as compared to B. So when these stars are viewed from opposite end of the Earth orbit, like opposite end of the Earth orbit diameter about the sun. So there will be change in the angular position will be there. So when we observe these stars, for 6 months, what we'll find the angular displacement, that is the angle. So angular displacement of B will be twice compared to A. And why the angular displacement is B is twice as compared to A? Because those objects which are closer to us, they appear to move faster as compared to an object far from us, or they appear to cover more distance as compared to object far from us if they are moving at the same speed. That's why trigonometric parallax is not, you cannot be used for stars which are very far from us. Reason is that if the star is too far from us, then apparent change in position, like example, this is a star, say X, when after 6 months it might change this position here. So for that 6 month duration, the change in angle will be very small. So it will have a higher uncertainty. That's why trigonometric parallax cannot be used for stellar objects which are too far from us. Is it clear this part? In part C, it was intended that Parkers would orbit the Earth directly above the equator with a period of 24 hours. Why this orbit was used? Like when we are observing, why we specifically use this orbit? Because with this, the communication, like normally, like it will be, if it is 24 hours, same as like Earth, so it will be a geostationary satellite. Means it will remain at the same point throughout the Earth. So when we observe this star, like example, say this is the observatory, or this is say this a position A is representing observatory here, and this is a satellite. So if a satellite is a geostationary satellite, so it means as the Earth is moving, the satellite will remain at all the points, all the positions will remain at the same point. Like if A is here, the satellite will be just above that. If A is at this point, the satellite will be just above that. So all the position, the satellite will remain above that. So it will be make it easy to communicate. That's why geostationary satellites are relatively easy to communicate as compared to the different communicating satellite which are not geostationary, they changes the position. So communication would be satellite would be easier as it is having a duration of 24 hours, so it will always remain above the Earth, or always remain at the same point above the Earth. Calculate the height of a satellite above the equator when in this orbit, the Earth mass and the radius of Earth is given. So what actually we'll do, and we already have the time periods. It's a similar question like a gravitational uh, Newton law of gravitation we did. So this is satellite. So this height we need. Radius of Earth is there. So first, like radius of Earth example, RE. So this first we find R, and then the total R subtract the radius of Earth will get the height. As this is moving, we have the time period. So from time period, we can work out the speed. So we have T is equals to speed is distance divided by time. So distance for a circular, that is circumference, so 2 pi r. This r is the total distance, 2 pi r divided by t. So we can, like this v is there, and time should be in second. That is 24 hours, so 84,600 second, or because it is 24, this will be 24 times 60 times 60, 86,400, sorry. 86,400 seconds. So we'll have this value. R is unknown and V is also unknown. But what we do, as the object is moving in a circular path, to centripetal force is equals to gravitational force. Centripetal force is mv square over r, and the gravitational force is given by capital G. The mass of the Earth, the mass of a satellite is small m, and radius is r square. So this also r. Now when we cancel out this r, will cancel with this r, and mass of a satellite cancel out. So we have the V. So we'll substitute the value of the V. When I substitute the value, V square is there. So when I substitute the value of the V, this will be 2 pi r divided by, if I don't substitute like 86,400 for t, just all in variable. So this will be square, the gravitational constant, the mass of Earth, and radius. Now when we simplify this equation, so this will be 4 pi square r square t is equals to G, the mass of Earth, and R. If we simplify for R, so it will 4 pi square is multiplied, other side will be divided. So it will be G MET divided by 4 pi square, and then R cube. And then just R will be equal to G, the MET divided by 4 pi square, and then take 1 by 3. We'll get this R, and this R is the total distance. Then you have to subtract, because R is equals to radius of Earth plus h. So if you need h, the total R, what you get, minus the radius of Earth. So just substitution is there. So G is there, gravitational constant 6.67 exponent minus 11. Mass of Earth is given in the question. Time period is also 24 hours, which is 86,400 second. 4 pi square constant. So take 1 by 3 of this. You will get R, and then subtract from the radius of, subtract this R, radius of Earth from this R. So we'll get the value for H. The next one is Hertzsprung-Russell diagram for a star cluster in our galaxy as shown. So you can see most of them are in main sequence, and then this region is about the red giants. Complete the scale for temperature. It's always like, look, it's always like double and half, like, and it is always in a decreasing order. So this will be double of that. So this will be 10 into 10 to the power 3, and this will be half of that. So 2.5 into 10. Always it's like this. If, for example, if the same, this is scale we want to complete, and they say this is 6,000. So this will be double of that 12,000, and this will be half of that 3,000. Then explain how the cluster shows, explain how we know that the red giant stars are large in size. How we know they're large in size? Because you can see the luminosity depends on, like, it's proportional to fourth power of temperature and the surface area, according to Stephen Boltzmann law. And that is actually like surface area, we can Stephen Boltzmann constant 4 pi r square, the radius of Earth, radius of star square, and t raised to power 4. So even though these red giants, they have a low temperature, the temperature is low compared to other. So temperature is low, but their size is big. That's why the luminosity is higher. So how we can show from this that the red giants have a larger size? So because if they, according to the scale, the temperature is low, so they should have low luminosity. But because they have a high luminosity, it shows their size is much bigger. Explain how we know that the red giant star that we did, and how this diagram shows the star cluster is neither very young nor very old. So we can, if it was very young, like If it was a younger, then most of them will be a main sequence star. There should be there are red giants, so it means it is not very young. And why it's not very old? Because there are no white dwarfs. Otherwise, if it was very old, then there will be white dwarfs here. Means we will find some stars in this region. Because first there will be main sequence, then red giant, and then turn into a white dwarf. So if it was very young, then what should be the sequence? There should be, we don't find these red giants. We'll find only main sequence if it was very young. If it was very old, then we will find the white dwarfs also. But there are no white dwarfs, so that's why it shows that it is not very young nor very old. Then question 6, a line of a hydrogen spectrum from a lab has a wavelength of 486 nanometer in the spectrum of a light received from a distant galaxies. Determine the velocity. So we have to determine the velocity. So redshift is equals to change in wavelength divided by original wavelength. And redshift is equals to the speed at which the galaxy is moving divided by speed of the light. So first we'll work out the Doppler shift. So change in wavelength 507, 586 divided by original wavelength 486. 507 minus 486 divided by 486, this will give us the Doppler shift. And after getting a Doppler shift, this is a Doppler shift times the speed of a galaxy divided by speed of light, which is 3 into 10 power 8. So this multiplied there, we'll get about 1.3 exponent 7 meter per second. So that's the speed at which this galaxy is moving. Is it clear, this one?